Okay. Yeah, so thank you, and let's continue. So I forgot to mention one important thing that from this Lapélian formula stuff, that maybe this very last step, which we did the last 5 minutes, is actually close to what Felix Pshititsky and Mariusz Urbański did in their 89 or something like this paper, who are in now excused absence. So I can just mention their name without being afraid that they will correct me. So, but this argument there was closer to that one. Okay, anyhow, so what we had is this Lapélian formula, which said that, okay, we are exact dimensional. We can express the dimension by using the orthogonal projection for first-number typical directions. And how can from this we deduce that for our system, namely under strong separation condition and strong irreducibility, and what's the third? Proximality. This quantity here equals to the Lyapunov exponent. Well, it's not so hard to see that it equals to the Lyapunov dimension, the Lyapunov dimension of a mu, which is the minimum of two parts, the entropy over the largest Lyapunov exponent, and 1 plus the entropy minus the smallest divided by the largest Lyapunov exponent. And by the strong separation condition, I don't need to be afraid of that these quantities will be greater than 1. So this equality will hold. It's easy to see that if and only if, so the Hausdorff dimension of mu equals to the Lyapunov dimension of the mu, if and only if the Hausdorff dimension of the projected measure equals to the minimum of a 1 and the entropy over the Lyapunov exponent. The largest Lyapunov, again, lower index. Sorry, I will try to keep on with the lower index. For Furstenberg, almost every direction. And actually, that this holds under these three conditions is a theorem by myself, Mike Hochman, and Ariel Rapaport. So basically, this one under these three conditions holds, even under milder conditions it holds, but the strong irreducibility and the proximality is somewhat needed for the business. The strong separation is not. You can just have much weaker separation conditions. But under these, we have equality. And the question is, how can we get this equality? And I want to give you a rough idea. So basically, the very, very rough idea is that, okay, a projection of a self-affine measure is more or less a self-similar measure. So apply Hochman's entropy growth theorem on it and hope the best. And this is exactly what happens, except that you need to work through lots of technical details. However, I don't want to do that. So let me tell you a few things. One thing is that let us look at how this measure looks like really. Well, in this projection, we still have not used how this says. So, okay, let us use that this measure mu is a self-affine measure, right? So instead of First, we are pushing forward it with respect to Fi, then we are pushing forward it with respect to the orthogonal projection. Okay? So it's more like pushing forward it with the combination of Fi and the projection. This guy here is a map, right? This guy is still an affine map from the plane to the real line, just not an orthogonal projection anymore. It's actually a scaled version of an orthogonal projection, where the scaling is the following. It will be Ai's transpose action on the V transpose times the orthogonal projection along the inverse direction plus some translation. Which translation, of course, depends on I and V, but I don't want to emphasize it how. Okay, so what it means that if you first apply an affine mapping and then the orthogonal projection is the same if you apply the orthogonal projection on the inverse, the inverse direction, I mean the direction acted on the inverse matrix, and then you scale it somehow properly. So actually, what we have here is that this guy, this is another kind of stationary measure equation, but it contains maps from affine maps from R2 to R. Let me try to be more precise. Okay, let us denote by A21 be the set of affine maps of rank 1, mapping R2 to R. I want a distance on them, so if I have two elements, phi and psi, I define the distance on them by taking the maximum over 3 points, and the distances of phi xi and psi xi. Where, what are these 3 points? Well, your favorite 3 points on the plane in generic position, and I actually let it be not on the plane, but on my self-affine set. Okay, they should be in generic position. That's what to show that this guy is indeed a metric on these affine maps. Okay. What else? Using this metric, we can define a very weird thing. We can define, using this metric, a partition, a countable partition Qm, which is a partition on this space A21 such that the diameter of these Qn is more or less 2 to the power minus n, and Qn plus 1 is a refinement of Qn. So we have this weird space of R2 to R affine mappings. Still we have something which resembles to a dyadic partition. If you ask me how on earth is it possible, don't ask me. There is a gentleman sitting on the second row because it's a theorem by Kaenmaki, Ariel, and Suomala. And under certain conditions, you can construct such kind of partitions, and very fortunate, all these things will be satisfied. So we have a dyadic-like partition on this space. Why is this space interesting? Because exactly such kind of maps are written here, right? This kind of combination is such kind of map. Okay, so let's see the following. How can I write this projection V of nu? Actually, instead of that, I can write it as a measure theta and nu. So instead of saying that, let me write it by yeah. So instead of having that convex combination, I will take here a probability measure on what? On this space of affine transformations, where this measure is just a very, very simple, some convex combination of Dirac-masses. And this measure is nothing else than the push forward. So I want exactly to see this convention, where I simply say that if this is a probability measure on A21, so this is a probability measure on this A21 set, and this is a probability measure on my plane, then this measure is nothing else than the integral of the push forward of the measure nu, where we integrate along these functions. Is it okay? It's again a kind of stationarity equation. Just now, again, just like in the previous stationarity equation, I replaced it with a more general measure on these functions. Okay?
It's not a stationary, it's like a push forward to
yes, it's a push forward. It's stationary if it equals to itself. But yeah, we like this equation. Okay. Yes, okay. And actually, instead of theta, we can define a bunch of measures. And we like those kind of measures who has more or less the same contracting ratio. Look at here. What is the contracting ratio of the map Fi? What is the contracting ratio, roughly speaking, contracting ratio of this map? It corresponds to this norm, right? The norm of the transpose matrix on this space. So if I want those iterates, collect all those iterates where corresponds to this v direction, and I want to collect all finite words. They are now finite words, such that the norm of this matrix product on V is, again, we love dyadic partitions, so I again want here dyadic partitions. But the previous symbol, if I remove the last symbol, then it will be strictly greater than that. So I'm collecting here all those guys whose contraction, all these affine maps whose contraction is more or less 2 to the power n. And then it will be still true that if I define my measure to be the convex combination of that guys, so probability I times the Dirac mass on this Fi, then I still can write nu, the projection of nu, in this form, right? I still can write that this is theta v dot nu. This is true for every n. Okay, why do we want that? Because we want to understand the dimension. How do we understand the dimension? Well, actually we have understood the dimension in one very, very strong way. We understand it that it's exact dimensional. And there is a theorem by Young who says that if you are exact dimensional, then studying the dimension is the same as studying the entropy dimension. Namely, this means that the dimension of this orthogonal projection, again, still for Furstenberg almost every direction, because for other directions we have no idea whether we are exact dimensional or not. This value equals to the limit as n goes to infinity of the entropy of V with respect to the dyadic partition. And this dn is the usual dyadic partition. You divide the real line to little tiny intervals, which length 2 to the power minus n. So, and this guy is summing up for all partition element D in Bn with a minus the measure of D times log the same measure. So actually, instead of the Hausdorff dimension, we want to understand this partition dimension, this entropy dimension, and this entropy using the dyadic partition. And here comes to the picture why this guy plays an extraordinary role, because all the components inside of this measure have diameter and have support at most 2 to the minus n. Okay, basically they fit into one, but at most 2 partition elements. So we have a very good control on that. But I have no idea where this converges, so let me just denote this value wherever it wants to converge it. So I know that it converges because it's exact dimensional and it's a theorem of Young. But I have no idea what the value is, so let me denote it by D. My goal is to show that this value D equals to that one. Okay, this is one thing. And what's another thing? Okay, but somehow I want to compare this diamond, this entropy here, with the entropy of that measure, that theta and V measure, with respect to that dyadic partition. It's not necessarily clear why I want to do that, but I want to do that. First of all, why? Because if I take the limit of this theta and V with respect to my dyadic partition on that A21 space, then I can say that this is more or less the same up to a little error if I push forward the Dirac mass on the origin and I check my usual dyadic. And by more or less I mean up to an error. And the reason is exactly the same, exactly what I said. So this guy here, all the mass here, contraction ratio more or less 2 to the power minus n. Right? So if I, looking at my dyadic partition of it with respect to that, then I can just, it's the same as saying that where the translation parameters are, And it's exactly the same as looking at in this dyadic partition. But again, another point that this is, all the components here has diameter at most 2 to the power minus n. This means that this measure is again comparable if I push forward, not that one, but my self-affine measure. Right? Because the dyadic partition cannot really distinguish that this point or this tiny interval is inside of it. Okay, of course, this tiny interval, this little push forward projection V Fi of nu can fit into 2 parts, but this is just an extra tiny negligible error. So what I get is that this quantity here wants to converge the same d value where this projection is converging. That's very good. So at least we can study this guy somehow. Okay, maybe questions? No questions, okay. So, the second observation is, lemma is saying that basically, how shall I formulate it? Yes, I shall formulate in the following. For every s greater than 0, there exists a subset of the projective circle. Don't forget that these measures are all the functions where this measure theta n v is supported has this form. Okay? This keep in your mind. So for every s, there exists a set on the projective circle, and there exists a constant which depends on s, positive, such that the dimension of this set is as tiny as you want, and for every direction out of this set, we have exponential separation for that kind of guys. So the distance here, projection V of Fi and the projection V of Fj is at least constant times n. And I can say here, this is true for every n, where these I and j are coming from this previously defined psi, so the contracting ratios are the same, they belonging to the same measure, theta and v. So why is it true? Basically it's a simple estimate, because if you don't want that, if you are saying that you don't have exponential separation, so you are smaller than c to the power n, then it says that all these distances are smaller than c to the power n, right? So you need to cover the gamma can be covered if I cover by every I, 1, 2, 3, and every I and j there. From this set, all the directions such that this projection with xi minus this projection with fj, this one is at most c to the n. And now, this is an orthogonal. How can it happen? It can happen only if these guys are lying very close to B, right? It happens if the subspace, which is formed by fi minus xi and fj minus xi, if the subspace, which is spanned by these two guys, the angle of them with respect to B is at most what? At most some other constant, c to the n times whatever c prime. Right? Where this other constant is exactly the original distance of these points.
For this, we use some of the hypotheses, like approximation?
No, nothing. I just use that this is my fi xi, this is my fj xi. And where is it close to zero? When v is coming from this little cone. Yes?
So is this span, it's span of one vector? Or
The span of this vector. So this is one non-zero vector, so it's a one-dimensional line, like us v. So basically we are looking at this, and we are on the plane. Don't forget that we are on the plane. So this is just this tiny cone.
So this is for all ij?
This is for all ij, this is for all little I out of these 3 points. But what's the best part? I have the power to choose c. So it doesn't matter how many functions I do have here, exponentially many by the way, that it doesn't matter how many I have here. I still can say that if I cover this set, the Hausdorff dimension can be pushed down arbitrarily small by choosing c very tiny. Why is it good? It's good because there is a theorem by Guivar. Do I pronounce, I'm pretty sure that I don't pronounce his name correctly. Guivar. Okay, yes, thank you. And so what follows that the strong irreducibility proximality together implies that our Furstenberg measure, our famous Furstenberg measure, has positive dimension. And why is it good? That there exists some S. Let me choose this S exactly the half of the Hausdorff dimension of my Furstenberg measure. And then the Furstenberg measure says that I don't see the exceptional set who are not exponentially separated with respect to the CS. So by choosing this S, it says that nu f sees exponential separation for some C. Tiny, but for some. And this is what we like because then we can handle the entropy of this theta NV. Don't forget that theta NV is this convex combination of Dirac masses of functions where I collect all the functions who are contracting in their projection along V by more or less 2 to the power minus n. Okay? So I can say that I can take my weird partition. It's a dyadic partition, but if I choose this C That C is not that C, there are too many C's here. But this C depends on that C, and if I choose it horrendously large, then what I will see here is that the distance of these points, all these centers of these Dirac masses are at least C to the n. Right? This guy is this 2 to the power minus whatever C is that C to the n. But this guy is independent of n. This is true for every n. So what do you see here? What you see here is that it converges to the usual entropy. This goes to your entropy, entropy over Lyapunov exponent, because we set it up exactly to that one. But it converges to the entropy of the Lyapunov exponent, because this partition sees each Dirac mass, each component in this sum as on its own individual. Okay, and what do we want? We want that this guy is equal to that guy. And we cannot get always what we want, so let's assume that this is not the case. Let's assume that this D, what we want, is strictly smaller than this minimum of the entropy over Lyapunov exponent. Well, if it's strictly smaller, then I can say, what can I say? I want to see what I can say. Yes, I can say that this entropy of theta nV, this conditional entropy, sorry, this is a Q, QCn conditioned on Qn, which is basically nothing else because this guy is a refinement of that guy. This is just nothing else than the difference of these two entropies is positive. Right? At least converges to the difference of these two guys, which is positive. That's, I'm certain to be able to say. And actually this guy here, actually this conditional entropy is actually an expected value of some weird random variable. So let me define a random measure. So let theta n, let's say, phi. Why is phi? Oh, I don't know. What's other good symbol instead of theta? Still means my eta. Eta nb, a random measure, such that the probability that this eta n exactly corresponds to this theta nv measures restriction to a q element and normalized it back, it is exactly corresponds to the theta n measure of this q for every q coming from this qn partition. So you basically divide your measure with respect to your dyadic partition on this weird space. And you pick one of these measures randomly. if you do so, then what you can see is that the expected value of the entropy of this measure with respect to this QCN partition is exactly that conditional entropy. Do I need a C here or not? Yes, I do. This is exactly that. Oh, by the way, it should have been divided by C, but it doesn't matter. And we know that this expected value is positive. That's all what we know. But what does this mean? Well, it means at least that there exists such kind of epsilon positive, such that the probability that this entropy of this random measure is positive, so greater than some epsilon, is greater than some epsilon for n sufficiently large. Of course, this guy is just in the limit is positive. So we have this only for sufficiently large measures. So the only thing what we get out from our assumption that D is strictly smaller than this one is the fact that we have a bunch of measures with positive entropy, with at least some positive probability. And basically, that's enough. Why is it enough? Because we can state the following theorem, that for every epsilon greater than 0, there exists a delta such that for every n sufficiently large, where how sufficiently large we are depends on delta and epsilon, such that for every n sufficiently large, yes, and if theta is a probability measure on my A21 space, such that every map in its support has contracting ratio, so let me denote it by norm, more or less 2 to the power minus n. The support of this measure has diameter also more or less 2 to the power minus n. The entropy of this measure is greater than epsilon. And furthermore, nu is self-affine. Then the entropy, if you push forward your self-affine measure through this nu, sorry, I made a mistake. And for every t. Sorry, these ones should have been different. No, my bad, sorry. The t plus n, yes, is greater than delta plus my entropy if I push forward it with respect to one measure, one function. Okay, let me repeat it again. You give me an epsilon, I will give you a teeny tiny delta, and claiming that for any very big n's and tiny t's, if you have a measure where all the mass has size and contractions 2 to the power minus t, and its support is also 2 to the power minus t, but it has positive entropy with at least epsilon, then the measure, the entropy of the measure nu, of this pushed forward measure, must grow by this tiny delta according to its original, because this is, what is this? This is just a scaled version of it. This is actually, if I just project it down in one direction, one typical direction, of course. This is just kind of scaled version. This is the original measure center. This is the adapted version of Hochman's entropy growth theorem for that setup. Of course, all the evilness and all the disgustingness and all the details are hidden here. In the self-affineness, you need to show that these measures satisfy a bunch of nice uniformity conditions. All of them are hidden there. But if you believe that it works so, we are almost ready. Why? We are almost ready. Because why? We have this d value, which we have seen already, that it's or projected measures dimension via this entropy. Now, let me decompose this thingy into the following way. This is the limit as n goes to infinity. I will just write, instead of this push forward measure, if I would push forward it with respect to that measure, but we know that it's the same because we are talking about self-affine measure. But instead of that, I will see that this is the dyadic measure conditioned on dn divided by 1 over Cn. Basically, if you just imagine always, so if you just replace this one with that one, keeping in mind that this one is a refinement of that one, that's just an easy calculation. So basically, you have the partition for C1 plus n minus you have the partition for dn divided by Cn. The first component goes to C1 plus C times D. The second component goes to D over C. So it's the same D. It's just the same thing I've written in different way. But we can use that this is an expected value. This is the expected value of my random measure. This is the expected value, yes, here. This is the expected value of my random measure theta n, right? So if you use the convexity of the entropy, you see that, okay, maybe not a limb, but a limb sup of 1 over Cn, the expected value of this random measure on nu d c plus 1n. Now here happens several constellations. Because this is a random measure, but each of the components there, again, made to have diameter at most 2 to the power minus n. So basically, the dyadic partition cannot distinguish this measure, essentially, who has diameter 2 to the power minus n from the Dirac mass at the origin. So this guy, this condition entropy, is not here actually. And on the other hand, what can we say? Now, substitute this t in your mind with c to the n. What do we know? We want to estimate this with that from below. Now, I only know one thing, that the entropy is positive for some tiny epsilon. So there is a measure which set tiny epsilon, where the entropy with respect to the original grows slightly. So what's the original? This is my measure. Let me write d plus delta. Right? My entropy growth with this tiny delta. On this measure, on this set of measures with probability greater than epsilon. What about the other part? Well, I have absolutely no idea. But I know one thing, that the entropy cannot decrease. So on the remaining part, its entropy must be at least d. What did we get? This is d times epsilon times delta. The entropy growth, although it should not have. So its entropy value must be as large as it's possible not to observe this entropy growth phenomena, and this means that our assumptions was incorrect. The dimension is the minimum of entropy over Lyapunov exponent, and we got the result, and I ran out of time, so thank you very much for your attention.
So I was looking at your paper for this result by paper. What's the name of the paper? I didn't see a reference to your paper. The result by paper, where can I find it?
Okay, I can give you that paper.
Morally, it's saying that.
Okay, I think we were referring to the Bouguereau-Lecroix book, and in the Bouguereau-Lecroix book, they are it's referring to Guillemard.
So just to clarify, so like morally, because there are like okay, so the external separation doesn't always hold for self-similar sets of line, but because we have some sort of dynamics, you would expect to have exponential separation.
Yeah, almost surely.
Almost surely.
Yes.
Yes.
Exactly.
It's like the same phenomenon that shows up in like.
Yes.
Okay.
Yes. Exactly. It's the same phenomena, like very similar. That if you have an iterated self-similar IFS on the plane, which does not have any rotation, then of course there are these exceptional dimensions. But if there is an irrational rotation, then actually your Furstenberg measure is still making sense. It's the Lebesgue measure. With respect to the Lebesgue measure, no one will ever drop, almost surely. And again, by some machinery introduced by Hochman and Schmerkin, again you can see that then nowhere will drop. So it's the same that if you can find this extra parameter, extra freedom in the business, then you can say even more that, okay, there are some exceptional directions which are small, but this extra freedom will just say that there is no exception. At least heuristic.
Let's thank Balázs again.
Thank you very much.
So this reference to Gavage, you're saying, it's in the book by Bogowald?
Yes.
Reference? Okay.
Yes.
Do you know the reference by Gavage?